Hello, I'm Rebecca Barnes, and welcome to the Science ESA vodcast. In this episode, we'll take a glimpse at the hot, energetic, and often violent universe revealed through X-ray and gamma-ray astronomy. We'll look at ESA missions that detect this hidden light and find out how the science these missions perform is meticulously planned. Beyond blue visible light and the ultraviolet region of the electromagnetic spectrum, the waves continue to increase in energy and decrease in length, to about the size of a molecule and then to the size of subatomic particles. These waves are X-rays and gamma rays, energetic and potentially dangerous to life. Due to their extremely short wavelength, X-rays and gamma rays cannot penetrate Earth's relatively thick atmosphere and must be observed by space telescopes. The era of high-energy astronomy really kicked off with the space age, exposing astronomers to violent phenomena that had been invisible at other wavelengths.
Any object heated to more than 1,000,000 degrees Kelvin will begin to give off significant quantities of X-rays. This is one of the many ways that high-energy radiation is produced. X-rays are often detected from a binary star system where one star is the extraordinarily dense remains of a stellar core in the form of a neutron star or a black hole. These objects have a huge gravitational pull which strips gas away from the companion star. As this gas spirals towards the neutron star or the black hole, it is heated to incredible temperatures, high enough for X-rays to be emitted. Supernova remnants also emit X-rays, and beyond our galaxy, large black holes are thought to power the tremendous X-ray emission from active galaxies. The gamma-ray universe is a place of constant change, and it can be extremely volatile. Observing gamma rays helps astronomers to understand how matter and radiation interact with each other, especially under extreme conditions where temperatures are hundreds of millions of degrees, where matter is very dense, or where magnetic fields are very strong. Gamma-ray bursts are amongst the most powerful explosions in the universe. They occur randomly and unpredictably. Short bursts are thought to be colliding neutron stars in distant galaxies. Longer bursts may be the very first supermassive stars now exploding as powerful supernovae, known as hypernovae. There is also a diffuse gamma-ray emission coming from our galaxy. This is where energetic particles, or cosmic rays, collide with gas in interstellar space.
Europe is one of the pioneers of high-energy astronomy. In 1975, ESA launched COS-B. This mission lasted for over 6 years and made an extensive survey of gamma radiation across the galaxy. EXOSAT, the first European Space Agency X-ray observatory, launched in 1983, made nearly 2,000 observations of a variety of sources during its 3 years in operation. To continue the venture into the high-energy universe, ESA launched XMM Newton in 1999. It is the most sensitive X-ray telescope ever built and performs spectroscopy of cosmic X-ray sources. XMM Newton has 5 X-ray instruments, 3 cameras and 2 spectrometers, as well as an optical ultraviolet monitoring camera. Focusing X-rays is extremely challenging, and for this task, XMM Newton has 3 novel telescopes that are very different from those used to focus visible or infrared light. The mirrors on board XMM Newton are barrel-shaped and coated with gold. As X-rays travel down the barrel, they graze the mirror at a very small angle and reflect. If this angle of incidence is too large, the X-rays would be absorbed by the mirror material. Each of the telescopes is made up of 58 of these mirrors, nested together like Russian dolls. This provides the largest possible surface area over which the X-rays are collected. Integral, or the International Gamma Ray Astrophysics Laboratory, was launched in 2002. This observatory studies celestial radiation that is 10,000 to 10 million times more energetic than the photons that reach our eyes from the sun and stars. Integral has a large field of view, allowing many gamma-ray sources to be studied in one single exposure. There are 4 scientific instruments on board the spacecraft. Of the 2 that study gamma rays, one produces images and the other is a spectrometer. The other 2 instruments are an X-ray monitor and an optical camera. Gamma rays cannot be focused by conventional lenses and mirrors, and in fact are incredibly difficult to detect. This is because they are so energetic they can easily penetrate almost anything. For this reason, the instruments on board Integral use a unique technique known as coded mask. A coded mask telescope is like a pinhole camera, but with not one, but many pinholes. Both XMM Newton and Integral are space observatories feeding astronomers from around the world with fundamental information about the hidden universe. An Earth-based observatory is used by many different astronomers and must be kept in the best condition possible. An observatory in space is no different, but everything must be managed remotely. This is ESAC, the European Space Astronomy Centre, the scientific heart of the European Space Agency. It is here, in the quiet surrounds of Villanueva de la Cañada, near Madrid in Spain, that astronomers and engineers work together to study all aspects of the universe. ESAC is where the science that the XMM Newton and Integral space observatories perform is carefully planned. Astronomers from all over the world can request observing time on XMM Newton and Integral to be used to look at their object of interest. Time on these observatories is highly valued, and both receive enough proposals to fill the available observing schedule many times over. Once the best proposals have been chosen, experts from both observatories meticulously plan what the telescopes will observe and when. To communicate these plans to the observatories in space, the teams at ESAC must work with ESOC, the European Space Operations Centre in Germany. From ESOC, the detailed instructions are transmitted to XMM Newton and Integral via antennae located at various ground stations around the world. As well as planning what will be looked at, the astronomers at ESAC play a vital role in receiving data back from these observatories. These data are received from ground stations by ESOC and then sent to ESAC, where teams process and store the data so that it can be accessed and used by astronomers around the world. In addition to information about the astronomical observation, data from XMM Newton and Integral also contains details about the health of the instruments on board and their performance. It is crucial that the astronomers at ESAC monitor how the observatories are functioning. If there are any threats to the instruments, commands to protect them can be relayed to the observatory in space. It may sound like the operations of the XMM Newton and Integral Space Observatories are a routine affair. However, this is far from the truth. The nature of the high-energy universe is that sources vary with time. An object that seems to emit a steady stream of radiation may have a sudden and violent outburst, or a new source may suddenly start to emit high-energy radiation. These events can disrupt these carefully planned observations. Any space mission exploring the high-energy universe must be prepared to react rapidly to a sudden and sometimes rare celestial event. Astronomers at ESAC are prepared to seize an opportunity not to be missed and race against time to capture the light before it fades. An alert is received by the teams at ESAC. They first check to make sure the spacecraft can safely be reoriented towards the new source. If the decision is made to make this special observation, the team must quickly start the process of reshuffling the planned program of observations. This series of new commands is then sent to ESOC in Germany for transmission to the Space Observatory. Vast amounts of information about the hidden, high-energy universe lie within the precious data available from ESAC. So what secrets does this data hold? And have profound new discoveries been made? With eyes that peer into the most energetic phenomena in the cosmos, ESA's XMM Newton and Integral Space Observatories have been setting records, discovering the unexpected, and helping to further our understanding of the unknown universe.
Invisible light, the star-forming region of the Orion Nebula, is a beautiful cloud of gas and dust. When XMM Newton looked into this cloud, it discovered a huge area of extremely hot plasma revealed in X-rays.
This was quite a surprise, this detection in the Orion Nebula, which was not expected. The Orion Nebula is a nearby region where young stars are created. And if you look to the infrared, you see basically a very big hole in the center, and it was simply thought that this is an empty space. Now we looked with XMM and find exactly a hot gas filling out all this hole in the center of the nebula. The surprising point is that this hole was filled basically from one single hot star, which emits an enormous wind and plasma wind and fills this whole cavity in this nebula.
A supernova, marking the death of a massive star, can be bright enough to briefly outshine an entire galaxy. These explosions eject the outer layers of the star into the surrounding space, causing powerful shock waves.
And with this supernova remnant, the people were able to determine the velocity of the shock front. And if you have the velocity and the distance, you can calculate back when the supernova explodes. And therefore we could prove that this supernova explodes about 186 after Jesus Christ, and there were records from China and most probably also in Roman books, records about this supernova, and therefore it's the oldest recorded supernova, and we could now with XMM Newton locate this supernova on the sky, which is not straightforward because at this time people were not using a coordinate system on the sky.
XMM Newton made the first detection of two bright iron lines in the X-ray spectrum from a supermassive black hole lurking at the center of a distant active galaxy. X-rays are produced as matter is drawn onto the disk surrounding the black hole and from reflection by the disk material. By studying the varying brightness of the iron lines and that of the direct X-ray emission, astronomers observed a lag time between the variations.
But it confirms basically this interpretation, because from the basic physics we expect the second line a factor about 20 weaker than the primary line which we saw before. Now we have both lines and get a unique view so completely near to a black hole.
Using data from Integral, astronomers have identified a particular radioactive isotope of aluminium that is produced in massive stars and released into space by stellar winds or supernovae.
And it's very interesting to astronomers studying massive studying stars and supernovae, because it gives a completely independent measure of how many of these supernovae exist, and allow to determine that about every 50 years we should have a supernova in the galaxy, although we haven't seen anyone in several hundred years now by our optical telescopes.
Integral's wide field of view can be used to study the entire region at the center of our galaxy at one time. This region, known as the galactic bulge, is rich in bright variable X-ray and gamma-ray sources.
There, we have every time that we can observe this during the year, we have a program to go back there every 3 days, once per orbit, and take a sort of snapshot, several hours of observations, and see what is happening there. And the fascinating thing is it changes all the time. That's the thing about high energy astronomy. You don't see the same sources all the time. You see sources appear, disappear. We even had one moment when all the known sources were off, and you started suddenly to pick up some very faint ones which you had missed before. And otherwise we see transients coming up. And this kind of information is then distributed from here and from our colleagues at the Integral Science Data Center to the world, and other observatories then often enough turn to these sources, follow up what they are doing, and add the information that we get from our monitoring.
Supermassive black holes have been seen by Integral lurking in many galaxies. When galaxies closer to our own were searched, surprisingly few black holes were found.
We would expect from other astronomical clues to see a certain number of such black holes, and the expectation was that, well, they may be a little bit enshrouded in gas, and so at lower energies, like with XMM, you would have maybe missed them, but once we turn Integral on them, which peers through the gas and cloud, we would see them. But now the evidence is becoming more and more clear that we are actually not seeing enough of them, which may either lead to that you need a completely different explanation for the high energy background that you have, or that people have to involve an evolution in time, that actually these things have changed over the evolution of the universe, and we're not seeing exactly the same sources now in more recent universe than we expect that we get from other information looking further back in time with other telescopes.
These really are just a small taster of the celestial wonders previously hidden to astronomers and revealed by these remarkable space observatories. XMM Newton and Integral will continue to keep watch on the ever-changing high-energy X-ray and gamma-ray universe, react to sudden, violent outbursts, and help to solve mysteries of the cosmos. I'm Rebecca Barnes. Thank you for watching the Science ESA vodcast.